Okay, so last time we have been looking at the conservation of energy equation for a control volume. And what we did is we applied the Reynolds transport theorem to convert a system point of view, once again, to a control volume point of view. And this is the equation that we finally arrived at. And on this side you have the time derivative of the energy inside the control volume, and you have this accounts for transport across the control surface. So this is your left hand side, and on the right hand side you have the energy terms that are being added to the control volume, right? So although this doesn't have the subscript, this Q dot is into the control volume, this W dot is also into the control volume. And we had seen that this expression of this E is equal to this particular form, where this U, please do not confuse it with the velocity. This is internal energy, and I'm sorry, but we just have so many symbols, so many variables, and we're going to run out of symbols. And unfortunately, most books also do this. They just recycle the same symbols again and again. So I hope this doesn't lead to any confusion, but this is your energy here. Okay. And while we were at it, we had said that this Q dot can happen due to many different causes, right? Heat transfer can occur due to conduction, convection, radiation, and you have to take all of them into account while calculating Q dot. Similarly, for the work done can happen in many different ways, and we have to take all of them into account. Now, when it comes to the fluid, we had said that it's easy sometimes to break up the work done into these three different forms, and these are quite commonly experienced. So that's why it's easy. This is something that is sort of natural, that we break up the work done into these three subcomponents. And the shaft work comes because you often have turbo machinery which will impart energy to fluid. It happens in pumps, it will happen in turbines and other places. This is work done due to other forces like viscous forces, electromagnetic forces, etc. And here you have the pressure work. So what we want to do is we just want to take a look at, let's say, the first expression, which is the work done by pressure on the control volume. So let us just draw a arbitrary control volume, and let's say there is a arbitrary small area dA, okay, and this is a infinitesimally small area, and the outward normal here is given by n hat, and the velocity vector here has some other direction. This is the velocity of the particles passing through the control volume. But this when this velocity, this material is passing with a velocity, there is a force that is also acting here, and on the control volume the force is in the negative direction to is opposite to the direction of the normal vector. Sorry, this red line has almost sort of intruded upon my n hat expression, but this is my P into dA force. So in a fluid, the normal force is given by P, so we have PdA, right? Okay, good. So now what is my work done then? So my work done due to pressure, okay, and I'm not going to write on CV, we understand that, we have been discussing that for enough time now, is basically the force times the dotted with the relative velocity. So what is the force here? The force is minus P dA with respect to the outward normal, right, dot UREL. So this is equal to minus P UREL dot dA. Now they are both in their vector forms. So if I want to find out the total work done, how will I do that? Well, I mean, there's only one way. You have a differential, so you'll just integrate, right? So you integrate both sides. So if you integrate the left hand side, you end up getting the work done term What happens when you integrate the left hand side? Sorry, the right hand side. Then you are integrating over the control surface, minus P. Yes. Okay, now that I've written this form, you might have sort of already guessed why I'm writing it like this. You see, there is a similarity with one of the other terms on the left hand side. So there is a portion of W dot that looks very similar to this. So what I can do is I can break up W dot and break up the term that looks similar to this onto the left hand side, right? Actually, that's exactly what we're going to do. So if you now substitute it there, what you will find is, so substitute it in the main equation. So substituting, you have your regular terms. So substituting into the energy equation. Okay, so the first term obviously remains, nothing changes in there. Now control surface, now I am going to write my E as E plus, we know E is U plus half V square plus GZ. We have discussed this part, right? Now there is an additional pressure term. Now here the pressure was minus, so when it goes to the other side it becomes a plus automatically. Now this one more quick difference between this term. Here there is a rho, but there is no rho term here, right? So this is actually going to be my P by rho. Okay, and this other term is obviously now common to the entire thing. Okay, so this is my expression. This is what my left hand side becomes. And on this right hand side, you have my Q dot plus you have W dot shaft work plus W dot other. Okay, so now what happens is we can define a term. Okay, so now what we'll do is, so we'll define a term called define H, which is specific enthalpy, and this H we will define it as U plus P by rho. Okay, or basically my U plus PV, where my V now is specific volume. Right, volume by mass. So this is another specific term, right? U was already specific, P has been made into specific here. So we'll define this term, and when we do this, so we can now simplify this equation a little bit more. And what I'm going to do is I'm just going to take this entire equation and so this, let's get rid of this thing. Now we'll simplify the term in the brackets here. So here we can say this is now equal to H plus half V square plus GZ into rho Okay, great. So this becomes an important equation for my conservation of energy. This is that conservation of energy simplified and transformed a little bit. This equation in this particular form is, we'll see, is going to be quite useful to us. Before we do that, let's look at some specific cases. Okay, so what we do is we look for certain specific cases. And let us first take the case where the flow is steady. Okay, so for a flow where total energy in CV is constant with time, basically steady, right? Okay. So I'm just writing that. Then all you need to do is in this particular equation, wait a second. So what will happen is you can write this equation now simply, but you can simply choose to ignore this term. Okay, that's the idea. So if you ignore this term, then we have only this integral equal to this particular term. And we are going to simplify it in stages, so we'll see why we are doing this. There is a reason behind this madness, but we'll see how it leads to a particularly useful form in a few minutes. But one more thing here is that when I say that this is steady flow, now you know what, this control volume can be composed of, maybe there's a pump in here, maybe there are pipes and all that, everything is in there, and that this control volume just covers that. And what might be happening is that the total energy of this entire system is constant with time, although there is some unsteadiness in the flow at the small scale. So for example, if you start looking inside the pump itself, where the veins are moving, so there might be an unsteadiness of flow there. But the flow can be steady at the global level. So the flow may be unsteady at the local level, but may be steady on a larger scale for the control volume. So you have to make a decision on whether this is applicable or not, depending on the particular scenario. Okay. So it's not just as simple as thinking whether the energy at every location is 0 or not. Okay. We'll make one more simplification now. So now we'll take this equation, okay, and we'll say that we'll constrain it further for the case of a single inlet and single outlet. Okay. So further, for the case of single inlet and single outlet, okay, then my conservation of equation. So now I can, when I have to do this integration, all I have to do is evaluate this integral at the endpoints, which is basically the inlet and outlet. So what I can do is I can write this above equation as h plus half v square. I'll make some modification in a second. Outlet minus h plus half v square plus gz inlet equal to my q dot by, okay, wait a second, okay, sorry, I've just forgotten a term here. So there is a term m dot outlet and there is a term m dot inlet here, and this is the same as the previous one. Now if you have a single inlet and a single outlet and the flow is steady, then necessarily these two m's have to be the same. Okay, so what we can do is we can actually get rid of these m's on this side and instead just divide this entire thing by m dot, which is the mass flow rate through the system. But still there is another problem here, which is here when I am doing this integral, this v need not be constant at every point across the control surface. But now this is this should be the average value of this. This is the total integral value, right? So this has to be, this v has to be denoted by bar to denote that this is some kind of an average velocity, right? And in that case, this term may not exactly be half. So what we will do is we will introduce the term alpha here, and this alpha will now be called the kinetic energy correction factor. Okay, so I hope this was this you understood, but let's understand it with a little bit more example. Okay, so we want to make sure we understand this. So let's say there is a pipe, okay, and there is a flow through this pipe. Now when we have a steady flow, single inlet, single outlet, how does this flow look like? Well, we have for laminar flow, we'll have laminar steady flow, we'll have a parabolic nice profile. So this is V. But V is a function of the spatial location. So when you do this integral, this V you have to account for the fact that V is varying at every point of this cross section. So what we are trying to do is we are trying to replace this V with another average velocity that we just multiplied with the m dot term, right, the mass flux. So this V bar is not going to be the same as V. So here, that is why we have to have an alpha term to account for that. So the correction factor accounts for the fact that the average velocity does not contain the same kinetic energy as a non-uniform distribution. Okay. So the kinetic energy, so basically what we are saying is that the kinetic energy of this non-uniform profile, the kinetic energy of the non-uniform profile is integral over A half rho V square into rho V dA. Okay, but this is not equal to some half m dot some average, the average velocity. Okay, this is not equal to that. So alpha accounts for that, and basically if you have to define it, is the same as half. So I'll just put this equation that we have written before. I'm sorry, I've written rho twice. Sorry, there's a mistake here. Okay, well, let me correct it. Okay, and I was going to repeat this mistake here. So this is and this is half m dot. Okay, so this alpha just corrects for that term. Now for a laminar flow, laminar flow through pipe, steady flow, where the cross section is parabolic, alpha actually comes out to be equal to 2. Okay, so this I'm going to leave it to you. Please do yourself and check. And as the flow starts becoming turbulent, okay, as flow starts becoming turbulent, alpha tends towards 1. You know why? Because what happens is, as the flow becomes turbulent, the flow starts to become more and more uniform. It doesn't look parabolic anymore. Okay, so if you want to later on, we'll see what, I think in the later half of the course you'll see what increasing Reynolds number does to this. Well, we have not even encountered Reynolds number properly yet. So later on in the course you will see that as the flow goes from laminar to turbulent, this profile changes. Okay. And when it changes, it becomes closer to 1. Okay, fantastic. So we are doing well on time. Okay, so there are a few more things I want to talk about. and this quantity H plus alpha V bar is GZ is also called, this quantity is also called the total specific enthalpy. And if Q dot equal to W shaft equal to W other equal to 0, then H T equal to a constant, right? Or in a situation such that somehow all these different terms, if they cancel out, okay, so the net work done, net energy added to the system is 0, then this total enthalpy remains constant. So when would something like this would happen? So for example, if the control volume surface, so if this surface is adiabatic, and if there were no pumps here doing shaft work, and there is no other work going on in the system, then your specific enthalpy would remain constant. Okay, so that's a useful rule. I hope that some of you, you are probably able to recall some of your undergraduate level fluid mechanics and see that this is, maybe you are getting a hint of where we are going towards. If this I hope this expression is reminding you of something. Okay, I mean, if you have forgotten, we'll come to it in a second, but still. Okay, now let's do one thing. To get to that place, let us replace this H with its original value, which was U plus P by rho. Okay, so to do that, okay, we get here and say U plus P by rho plus alpha V bar square by 2 plus GZ at outlet minus U. So we are continuing with the same assumption of steady flow and a single inlet outlet. So we are just going on and seeing how far we can simplify whatever expression we can get, right? And this is your Q dot by M dot plus W dot shaft dot M dot plus W dot other by M dot. Okay, so what I'll do now is I'll take this U's onto the other side, okay, just to make my life easy. So this would help with a few things. So I'll take my U over to that side, and what I can do now is I can write P by rho plus alpha V bar square by 2 plus GZ at the outlet is equal to, now, is equal to my P plus rho plus again this entire term GZ at the inlet, okay, minus, and now we are just going to put this into the a slightly different form, and there's a reason why we're doing minus, and this is equal to minus Q dot by M dot. We're retaining the signs, proper sign, and this is M dot W dot shaft and W dot other by M dot. Okay. Now it's traditional to actually divide by G also, and so if you divide by G on both sides, so just make this Z and make it 2G. This will become 2G. This will be a G here, a G here, and then divide this entire term by G. Divide, you have a G here. Okay. Now this particular term is also called head loss. written as H subscript L, and it's basically the head loss due to the heating of the fluid. Okay, this term, I'm probably going to run out of space here. This term is also called the shaft head. The head is nothing but a component of the energy due to a certain thing, and the energy written in a certain way, right? So, okay, I have run out of space. So let me just go to another page, and what I'll do is I'll just write it here with another color maybe. Okay, W dot, what I was left with other dot M dot G. This term is also called the other head, and we'll maybe just say HO for that. P by rho G, this is also called the pressure head. And V square by 2G is also called the velocity head. And Z contributes to what is called the elevation head. Great. So our final great equation is now in the form of different heads, which are basically the different contributions to the energy, and part of the contribution comes due to the pressure, another one comes due to the velocity, the height, and this is the loss due to the heat. This is the addition of head due to shaft work. This is again the addition of head due to some other work. So I can just reformulate this entire equation, and now I can write it as P by rho G plus alpha V bar square by 2G plus Z at outlet is equal to my P by rho G plus alpha V bar square by 2G plus Z I minus HL plus H of shaft, which I wrote as HS, and this is H0. This is a rather important equation, and people come across it a few times. I mean, did you see this coming? I told you a few minutes ago that we are most likely charting known territory with respect to what you have probably seen in your undergraduate classes. So this is also called the extended Bernoulli equation. By the way, a fun fact about Bernoulli, well, I mean, you will come across Bernoulli's name quite a few times in different parts of mechanics and fluid mechanics and other things, and but this Bernoulli is not always the same Bernoulli. There are many Bernoullis who contributed, who worked, and there was an entire family, and they all contributed, and most of the time I can't remember which Bernoulli contributed to what. But all of them, there are many phenomena which have this name of Bernoulli, and it's just so confusing at times. But well, I guess one good advantage of having such a family, family name is everything gets seems like the work done by one person, but that's not true. Okay, so we have come to a very important equation. And this equation was derived from the conservation of energy equation, but under special circumstances. And the special circumstances are that this is for a steady flow with a single inlet outlet, and then you can divide up the energy into different heads, and there is a contribution due to pressure, there is a contribution due to velocity, there is a contribution due to elevation. And there is a loss term here, which is due to, let's say, the the heat that might be lost from the your fluid, and shaft work which might be added to the fluid, and another head added to the fluid. By the way, this minus HL, this is just traditional, okay, so we have deliberately done this minus sign here and introduced this, so that's just a traditional way of doing it. Okay, so we have seen the extended Bernoulli equation, and this is quite good because it adds to our understanding of fluid flow in many complex situations, and we can quickly apply the extended Bernoulli in some cases to evaluate simple expression, to just get simple estimates of velocity or other pressures, etc. Okay. Well, one final thing maybe I'll just quickly comment on, which I find also was in the book. So if there's a body force, for example, so let's say there's a body force on CV, then the work done due to the body force can be written as U dot FB rho dV, okay, where FB is the body force per unit mass, and this U is just the velocity, right? So this is the net body work done due to the body force in a given fluid. Okay, so you can add other terms like this and go ahead and compute your this entire relationship and apply the conservation of energy. Sorry, I'm just looking for this. Yeah, apply the conservation of energy for different cases, for different problems. Now, what I've done is I've deliberately worked out a problem for you. Okay, and what I'm going to do, just like last time, I'm not going to work out the problem here in the class because it takes quite a lot of time. So I'll just briefly describe the problem, but the solution is already worked out, and I'll give you the PDF. So you can go through the PDF and understand it. And anyway, I'm just going to quickly skim over the problem. The problem is simple. There is what you are given is that there's a large room. There's a large room which has 150 people in it. Each person is dissipating 60 watts of heat. Okay, and you have sources of light in the room, and there is incoming radiation due to this light, and this is contributing to the energy coming into the room also. So there is an energy input into the room due to the light, and that is around 4 kilowatt. Okay, so in terms of power, and the room walls are given to you as a diabetic, and there is an AC system that is going on where the intention is that the air should come in at 15 degrees Celsius and should leave at not more than 25 degrees Celsius. Okay, so then the question is, what should be this m dot to maintain this kind of a condition? So incoming, as I said, incoming room air is at 15 degrees. To simplify ourselves, we will say that the return air right now is at 25 degrees, and we will try to see what m dot will lead to this 25 degrees Celsius. Okay, so the control volume that has been drawn, it does not include the source of light and this people, so it just goes around, and this is the room. And if we, so this is, by the way, for us, so now we'll assume that the flow is steady, obviously. So we'll just get rid of this term and just straight up use this one. There's obviously no shaft work, no other work, so there's only Q dot in. Now this Q dot, if you calculate, its contribution is due to the people and due to the light. That comes to be around something like 9,000 watts. Now how do you evaluate this term? Now again, as I said, this was just like that previous plan, situation where we have a single inlet, single outlet, right? So in our case, this entire thing is equal to m dot h outlet, m dot h minus m dot h inlet. And remember that because it's a steady state, m dot inlet and m dot outlet are the same. So this m dots are the same because it's a steady state condition. Okay. So if you go ahead, then and then later on assume that there's an ideal gas. So this is the expression that you will get, and you have to find out the denominator. If you need to find out the denominator, you are free to assume that the air is an ideal gas, and the relationship with the temperature is given as Cp, T outlet minus T inlet, where Cp is the specific heat of the air at constant pressure. Okay. So, and right now to simplify your life, I have given this value of Cp as 1000 joules per kg per Kelvin. So then you do your math, it should come out to be around 1.3 kgs per second. So I hope this does come out to this value, and if it doesn't, you let me know. Okay. Now what we will do is we will go. Wait a second. Where are we? Okay. Right. Okay. So we have been discussing all these equations. We discussed the integral form of the equation for a situation where you have conservation of mass, conservation of momentum, and conservation of energy. Now, these were all done with respect to an inertial reference frame. Oh, sorry, obviously we also did angular momentum, right? Now, Newton's second law holds strictly for the inertial or non-accelerating frames of reference. So, what happens when we consider frames of reference that are not inertial, which means that they are accelerating? So, to do that, we have to borrow a relationship from dynamics. I'm not going to work out the entire relationship, but I'm just going to give you the basic setup. Okay, and maybe I'll just use a new page. So this is a new topic, not a new topic, but just for the old topic, non-inertial frames of reference. So let us say that you have a reference frame which is given as capital X, capital Y, capital Z, and then there is another frame of reference X, Y, Z. Okay. And there is, let's say, a particle of interest, and now this particle can be described in terms of the capital X, Y, Z frame of reference, which is, let's say, the R. So this will be, let's say, R, capital X, capital Y, capital Z, and in this coordinate system you will have the radius vector will now be R, small x, small y, small z. Okay, and the radius vector for this, so you also have to track this frame with respect to the other one, and this is for the tracking of the frame. This is small x, small y, small z with respect. Okay, I'm running out of space. Wait a second. Sorry, let me just write it somewhere else. So this is my R, small x, small y, small z with respect to capital Y, capital X, capital Y, capital Z. Okay. So this R in X, Y, Z, you can either evaluate it, the particle with respect to the X, Y, Z reference frame, or you could evaluate it with respect to the small x, small y, small z reference frame, but then you have to account for this other, one reference frame with respect to the other one. So this is what the equation looks like. Okay, so now this other reference frame with respect to this one can translate or it can even rotate. Okay, so both can happen. And if you want to calculate the acceleration, so if you want to calculate, let's say, the velocity u in the xyz reference frame, then what you have to do is, so by the way, I'm skipping a lot of vector algebra here, and you're free to work it out yourself, or if there is enough time in the class before I finish all my required material, I will also discuss that, or else you can look up a book of dynamics where this will be given. So this u, which is the velocity in capital X, capital Y, capital Z reference frame, is given as the velocity of the xyz, the small xyz reference frame with respect to the capital X, capital Y, capital Z reference frame, plus u as measured from the small x, small y, small z reference frame, plus theta dot or omega. Basically, some places you'll have omega xyz with respect to the capital X, capital Y, capital Z cross r. And this is again this is vector small x, small y, small z. Okay. So this is interesting because it doesn't have the other term. So you are free to try and work this out. Similarly, you can do for acceleration, and for acceleration what you will find is capital X, capital Y, capital Z acceleration with respect to this reference frame is equal to the acceleration measured in the xyz reference frame plus the acceleration of the xyz reference frame with respect to the capital Y, capital Z capital X, capital Y, capital Z reference frame plus theta double dot x, y, z with respect to x, y, z, capital X, capital Y, capital Z. That's what is in the cross r small x, small y, small z plus. This equation is a bit cumbersome. So, by the way, I don't expect you to remember this equation. So, if required, I'll just give it to you in an exam. So, don't worry. Don't try to memorize this. If you can, then try to find a book on dynamics and see if you can find this equation and understand why it comes about, or try to work it out yourself. But I don't expect you to be memorizing this. I have not memorized it either. Don't worry. Right now I'm just copying from one of my notes. Theta dot xyz divided by xyz, not divided by, sorry, with respect to r small x, small y, small z. Okay. And I mean, you can do it in any order you want. I just choose to place the brackets like that. And this particular so this is basically the rectilinear acceleration, and this is the rectilinear acceleration measured in the other frame, and this is with respect to the rectilinear acceleration of the particle in the of the frames itself with respect to the other frame. And this is this particular term is also called the Coriolis term, and this is finally the other one is a centripetal term. Okay. So this is how you have to deal with non-inertial reference frames. So remember, let me just see how we are doing on time. Okay, I'll just end it right now, this particular portion, and then I'll start off with one of the sample problems in the next set. Okay.